Students, welcome you all in today's video in which we will study more detail about the polarizability. As in the previous video, I have already told you about polarizability, what is polarization, that how an oscillating electric field, when it falls on your molecule, it also oscillates your molecule, that is, it produces some kind of motions in the molecule that leads to the polarization, that leads to the displacement of the electrons in your molecule, right? So today we will study that how that polarizability, how that displacement of electrons, it affects the polarizability that leads to the change in polarizability. So if suppose just that if I have a molecule like this, okay, so I am applying the field parallel to this axis, right? So here I have already I have already told you in detail that when the field is parallel to the molecular axis, so in that case polarizability is higher, right? So now as this field is oscillating, not static, so definitely your molecule will show some kind of motion, and that motions are vibration and rotation motion. So field is still coming in this direction, your molecule start rotating. Now the electron pair in this molecule, they are not parallel to this field. Okay, so therefore the distortion of these electrons become bit difficult. So now when field is totally perpendicular to this axis, there will be least polarizability. The distortion of the electrons is not possible at all in this case. Now the polarizability factor again started increasing as soon as it will attain the this position, that is when your electric field it is parallel to this molecular axis, right? So you can also see there in this structure AB, when it start rotating, AB, some molecule, when it start rotating, so you can see the change in the axis, and indirectly it will affect your polarizability factor. Okay, so that means polarizability is also not the same, not static, so you can't write on simply alpha all the time. Okay, so alpha was okay when it the field is static, right? So when your polarizability is changing, so that can be represented by this, that alpha is equal to alpha naught plus beta cos 2 pi mu vibrational t. Now mu vibrational means the frequency with which that molecule start vibrating when the oscillating electric field it falls on the molecule, so it start vibrating, it start moving with some frequency. So that frequency is the vibrational frequency. Alpha naught here is the equilibrium polarizability. Equilibrium polarizability means when it is not vibrating. So as soon as oscillating electric field hits that molecule, it will start vibrating, and that change of vibration, that change of polarizability, that is given by this beta. Okay, so beta will give you that how readily the displacement of electron takes place when the oscillating electric field it hits that molecule. And mu vibration already told you, that is the vibrational frequency of the molecule. So now you have value of alpha as well as E. So you have mu is equal to alpha E, and alpha, you can put the value of alpha here from this equation, that is alpha naught plus beta sine mu vibrational, this is of molecule. Okay, this is the frequency of molecule T, plus you can also write down the value of electric field which we already derived before, that is E naught sine mu T. Here the mu is the frequency of your field, electromagnetic radiation. So you can say that first factor, it can gives you the polarizability due to inner motion, that is due to the motions in the molecule. And the second factor, it gives you the polarizability due to changing electric field. So both of these factors, they will further they will further leads to the dipole moment production in your molecule. So we have another derivation, another, we are going to just open this equation. So what you have to do is, for that, in order to just specify that which factor is for Stokes line, which factor is for anti-Stokes line, because this whole equation of dipole moment, that is for your Raman scattering. This whole equation is for Raman scattering. In case we have some field is coming, okay, and hitting the molecule, then that the scattered photon, it has different vibrational frequency as compared to the incident photon. So for that case, in that case, we are going to specify that which frequency is for Stoke line and which frequency is for your anti-Stoke line. So just we are going to do is we are going to multiply. We are going to multiply this E naught sine omega t firstly by alpha naught and then by beta sine omega, beta sine mu t, right? So if you multiply this factor, so your equation will become this: alpha naught E naught sine mu t plus alpha naught beta sine beta E naught sine mu t, and you can also write down the here the value of beta, that is beta sine mu vibrational t, right? So you can also see this on the screen. So now we are going to apply the formula, that is cos A cos B. Now here the A is your mu vibrational, is your B, and your mu is A. Simply you are just going to put the formula, your values in the formula. So I'm just going to take this common E naught and beta. So we have in the formula we have half, as you can see here, that cos A cos B is equal to half cos A minus B plus cos A plus B. So I'm just going to put the values of A and B in this formula, and I will get this equation, that is mu is equal to alpha E naught cos pi mu t plus half E naught beta, and the whole mu minus mu vibrational and mu plus mu vibrational t. So here the first factor, that is your first term, that is alpha naught E naught. Alpha naught already told you, that is the equilibrium polarizability, right? When there is no vibration, no change, no rotations in your molecule. So that is the case of Rayleigh scattering. So in that case, just your incident photon, it hits the molecule and it goes with the same frequency. No change in the energy takes place. So first your term, it represents the Rayleigh scattering. And your second term, that is your mu minus mu vibrational, that is for your Stokes line. Stokes line means when your scattered photon, it has the lesser energy as compared to your incident photon. And the third term, that is your mu plus mu vibrational, that will give you the anti-Stokes line corresponding to the anti-Stokes line, that is when your scattered photon, it has the more energy as compared to your incident photon. So lastly, we are going to discuss one more case, that is if we consider that there is no change in the polarizability, that is Rayleigh scattering. So in that case, you can also just take this equation in that way. The first term, why I have written Rayleigh scattering, that if polarizability, okay, there is no change in the polarizability, so you have to put this factor beta, because beta gives us the rate of change of polarizability. Now I am saying, I'm taking the case if your incident photon just hit the molecule and there is no change in the motions of, there is no oscillation takes place in the molecule, there is no polarization in the molecule. So in that case, beta's value will be 0. There is no rate of change of polarizability. So just put the value beta 0. So we will left with only this equation, that is mu is equal to alpha E naught sine 2 pi mu t. So simply this is the case of Rayleigh scattering, and so we can conclude from here 2 points, that Raman active, for Raman scattering, it is necessary that the polarizability change takes place. There will be some the magnitude of polarizability, and moreover the direction also affect the Raman scattering, Raman effect. Okay, so direction and magnitude of polarizability, both these factors, they will depict whether your molecule is Raman active or is Raman inactive. So this was all about the polarizability in detail. In the very next videos, we are going to pick up some molecules and we are going to compare whether they are Raman active or whether they are Raman inactive. So till then, thank you so much. Keep sharing, keep subscribing, keep liking, commenting on the video. Thank you so much.